So quiz is due tomorrow, October 1st at midnight, right? It's 10 questions, multiple choice. Remember, you can work together. You can use your notes. If you work with someone from another class period, that's okay. You guys were given the same quiz, but the questions are in different order. So don't just be like, yeah, number 7 is B, number 8 is C. You know, don't do something like that because that's not going to work. But give the same questions. And then I need a day. I need today to figure out the schedule. I'll kind of update you on when our next test is and all that stuff once I know, okay? But we've got to make up for some time. We're going to work today on this stuff. Please stay with me. Please pay attention. Don't be distracted by other things. And we're going to get a lot done. We might even get the homework done in this class because we always have a little extra time in this class. But we'll get to a point where if, at the very least, you'll just have a couple multiple choice questions to do as homework, okay? But I do have to teach all periods, so stay with me. So if you remember, you probably don't, maybe don't, but a couple Fridays ago was the last time I taught you, we did day 1 of this, and we learned about vertical asymptotes and holes. So everything I taught that Friday is covered in this lesson too, so you'll get a review of that or learn it for the first time, and then we're going to take it a little bit further, okay? So if you remember, rational functions are a fraction. And in that fraction, there's factoring. So it's like all the F words that we hate in math. And they're complicated. There's a lot of moving parts. They're all different. So, you know, we're starting out every single problem by saying what X is not allowed to be. So when you look at a rational function, if it's already factored for you, yay. If it's not, it has to be factored. And what we're going to do is focus on the denominator. We look at the denominator because we can never have what in a denominator? 0. Never can have 0 in a denominator. So what would make my denominator 0 in this problem would be -3 and -5. Those are the two numbers that if I plug them into this function would give me a 0 in the denominator. That's bad, okay? And someone asked last period, so let's just talk about it in case anyone's thinking it. Why do you switch the sign? I'm not switching the sign. I'm assessing what number, if I plugged it in for x, would make a 0. So when I put a -3 in plus 3, that would give me 0. That means -3 is a bad number. Once we establish what the bad numbers are, we have to give the bad numbers a job on the graph, okay? On the graph, bad numbers have a job of either vertical asymptote or hole, one or the other, okay? You have to be one or the other, okay? How do we tell which one you are? If you cancel, you're a hole. If you're left over in the denominator, you are a VA. Notice I haven't said anything about what's in the numerator, okay? We'll talk more about that in a minute, but the bad numbers always come from the denominator. So we have 2x plus 3's on top and 2x plus 3's on top, 3x plus 3's on the bottom. So we're going to cancel both of those on top, and how many will be left on the bottom? Just 1. Okay? So where the confusion comes in for a lot of us is when we have this multiplicity. Wait, you said when you cancel, you're a whole, and when you're left over, you're a VA. And we did both in this problem. So we canceled 2 of them in the denominator, but there's still 1 left in the denominator. We canceled and we have 1 left. And that's when I showed you guys this visual to help you guys understand who wins in the situation. Vertical asymptotes beat out holes. And in a minute, we'll talk about holes beating x-intercepts. So when you have to decide, did I cancel or is it left? It's left. If that number is left in the denominator, it is a vertical asymptote. Okay? And we do have a -3 left in the denominator. And x plus 5 doesn't cancel with anyone, so we have a second vertical asymptote. You can have more than one vertical asymptote. You can have more than one hole. You can have one in the other. Bottom line is both of our bad numbers have to be assigned a job, whether it's VA or hole, depends on if it cancels or not. That's it, okay? Look over here. We have x can't be what, look at the denominator, can't be -2 or 3, right? Those are the two numbers that would make a denominator 0. Now let's decide what their jobs are. So x plus 2, there's 3 on top and 1 on the bottom, right? So I'm going to cancel this x plus 2. How many are left on top? 2. So if you can just write over it, that's fine. You don't have to rewrite it. And same thing with the x minus 3. There's 1 on top, 2 on the bottom. So we'll cancel this one, and that'll leave 1 on the bottom. So now let's tell these guys what their jobs are. If you cancel, you are a whole. And we definitely canceled the -2. right? That canceled. And the VA is still in the denominator. That 3 is still in the denominator, so we have a VA at x equals 3. If you're left in the denominator, you're a VA. If you canceled, you're a whole. Now, I want to remind you that a whole is literally an ordered pair. We know the x value. In our next example in a minute, we're going to find that y value, but I just want to remind you of that here. Also, this is a good chance to tell you about x-intercepts. X-intercepts come from the numerator. Okay? Any x's that are in your numerator are going to give you an x-intercept, unless they were a whole or a VA to begin with. So look, if you look here, see how we canceled some of the x plus 2's with this x plus 2, and that created a whole at x equals negative 2? Well, let's pretend we didn't have any of that, and I just gave you y equals x plus 2 as my problem. You would say, oh, there's an x-intercept at negative 2. But you can't be an x-intercept and a whole. You can't be both. It's already been assigned as a whole. That number is already a whole. You can't now be an x-intercept as well. That's how the whole beats the x-intercept, okay? So vertical asymptote always beats a whole, and a whole always beats an x-intercept, okay? In this next one, we're not factored, so we must factor. First step of all factoring is to factor out a GCF. And sometimes you can do more, like this one. We have the difference of two squares. That's x plus 3, x minus 3. And you can't even do that first step until you're factored. This is where we can now say what x can't be. X can't be 3 and negative 3, but also 0. This x produces a 0. So those are the three values that would cause a problem. What type of problem depends on if you cancel or not. So this x right here, guys look, this x is going to cancel with one of these x's. Okay? So if you cancel, you are a whole. We will have a whole at x equals 0. And a vertical asymptote at the other two, because neither one of these are going to cancel with anything in the numerator. So we would have x is plus or minus 3, or you could write it out as x equals 3, x equals negative 3. Question? Ask it. If you're thinking it, somebody else is too. Ask me. Did you have a question? Okay, I'll go slower on this one, and I'll focus on you. All right. In my numerator, so I'm going to start out by factoring. Okay? So my numerator is x plus 5, x minus 5. And that's a chart problem. I'm asking myself what two numbers multiply to get 30 and add to get 11. 5 and 6, good. Okay, so right here, Evan, I'm going to focus on my denominator. I'm going to decide what x can't be. What will make my denominator 0? So, Evan, what number would make this guy 0 right here? No, 0 plus 5 is 5. Negative 5. And what would make this guy 0? Right, so those are my two bad numbers. Just the denominator. Numerator can be anything it wants. It can be 0, negative, fraction, it doesn't matter. Okay, now, what type of problem are these going to look like on the graph? You have to be one or the other, a whole or a VA. So we have to give those to an assignment. You're either a whole or a VA if we graphed it. How do we tell? Well, if you cancel, you're a whole. So we will have a whole at this number, x equals negative 5. If you're left in the denominator, meaning you didn't cancel with something in the numerator, you are now a VA. It's almost so simple that we overthink it. So I'm not trying to call you dumb if you're not getting it, but it's literally you cancel or you're left. One or the other. If you cancel, you're whole. If you're left, you're a VA. And we're going to continue doing that with more steps, okay? Now, I'm going to read this paragraph to you. When a rational function produces a whole, this point does not exist on the graph. That's why it's a whole. It doesn't exist, okay? That is, the x value and y value do not exist. That point, when you see it on the graph, is going to have it's going to be an open circle. That's a hole. It's actually a point that you can't have, so you make it open. It excludes it instead of includes it in the graph, okay? And so when you plug that x value into the rational function before simplification, you get a 0 in your denominator, which is bad. It's called the indeterminate form, but don't worry about that term. So how can we find the y value? Because remember I said we're going to have to find that actual point, okay? We need to know the whole point, not just the x value. Where does it happen? And so that's what this is saying is you're always going to plug into the simplified version of the function. So let me show you that on the next page. Okay? Go to the next page. So let's start the same way we did the other problems. We're just going to do 2 of these, okay? Let's just say what x can't be. X can't be -1 or 1, right? Look at your denominator. Those are the 2 numbers x can't be, right? Let's give them a job. If you cancel, you're a whole, okay? So we're going to have a whole at x equals what? What numbers would make that a whole? 1, right? What is the number that if I plug in there gives me a 0? 1, right? That's what we canceled, the 1 minus 1. Okay, we're going to find the y value in just a minute. Let's just finish this other part. And we have a VA at x equals -1, all right? So that part is what we were just doing in that last example. Now we're going to take it 2 steps further. We're going to find the y value, and then we're going to write a limit statement for that, all right? So in this fraction, after we canceled, we have a simplified form of the function, right? That's what's left over after I canceled. That's called the simplified version. We are going to plug our x value right into that and simplify it. Whether you show the work, do it in your calculator, do it in your head, is up to you. And that is where that open circle would be. On the graph, to the right one, up one, we would put literally an open circle to show that it is excluded from the graph. Okay? Now, we're going to write a limit statement for this. Limits are a huge part of the math from here on up. Okay? So let's talk about it. We always start by writing LIM, however you do it, cursive, not whatever, of whatever the name of the function is. So that will change from problem to problem. Just look and see what the name of it is. Okay? F of x, g of x, Sally, whatever. Okay? So limit of f of x as x approaches something. And we're going to have something right there. We're going to put something right there, equals, and we're going to put something right there. What I have in blue is what you're going to write 100% of the time. You always start with LIM. This will change the name of the function, okay? It's always going to be the letter X here with the approaches symbol, okay? That is going to be standard every single time. The only thing that's going to change is the name of it and what we put here and here. We're going to write a limit statement from the left and from the right here. Okay, so here's the thing. What is the x value of our whole? It's 1. So we're going to approach 1 from the left and 1 from the right. The order you write them in doesn't matter. I always do left first and then right. That's how I read a graph, but it doesn't matter. But remember, that negative symbol means from the left, positive symbol means from the right. What y value are we getting close to? And I'll show it to you on a graph here in a second and send it home. But what's the y value that's going to go right there? It's also 1 because of this, only because of this. They happen to be the same number. Annoying, but it's fine. So let me show you that graph I was looking at before. If I was talking about this point, as I approach -1 from the left and as I approach -1 from the right, okay? So I'm approaching -1 from the left and -1 from the right. What is the y value that I'm getting really, really close to? In this case, 8/5. Okay, so it's almost just like a kind of like a fancy way of writing the ordered pair for your whole. It's the x and the y value of your whole. Okay, let's do another one. X can't be, look at your denominator, -4 and -2. Those are the numbers that make my denominator 0, right? Those are the problems. What type of problem? Okay, let's look at the canceling stuff. The x plus 4s cancel, right? That means I'm going to have a whole at x equals negative 4. We know it's going to be an ordered pair. We'll find that in a second. And the VA doesn't cancel, right? X plus 2 does not cancel with anyone. So we have that. Riley, come on, can't sleep in here. All right, so I'm going to plug into this simplified form, which is x minus 3 over x plus 2. You have to plug into this simplified form. If you plug into the original, you're going to get a 0 in your denominator. So you'll know you did something wrong at that point, okay? So show as much or as little work as you want or need. Just be careful when you just plug the numbers in. I'm plugging in negative 4 for my x's. That gives me negative 7 over negative 2. Did I do that right? Yeah. And if you put that in your calculator, it's going to give you 3.5. But you could leave it as 7/2, or you could do 3.5. Any of those are perfectly fine. When we're working with graphs, though, it is much easier, because in a minute we're going to have to graph. It's easier to use decimals, because I can tell where 3.5 is, but where the heck is 7/2, right? Like, what does that mean? Right? Now let's write a limit statement. So set it up. The limit of, what's the name? G of x. It's always going to be x approaching something equals something. And we're going to write one from the left and one from the right. What? What's a mistake? And your x is for x approaches, it's just the x value of your whole, which is negative 4. From the left, from the right, coming from two different directions. What's the y value we're getting really, really close to? 3.5. Okay? We're going to practice those more together in a moment. We have 2 examples left. Okay, continuing with limits, go down to example 8. We are given some limit statements here, and what we're going to do is write a function, an equation, that matches that. Okay, sounds hard, it's really actually not. Okay, so I can see that the name of this guy is f of x, and I know it's a rational function, so it's going to be a fraction. So that's 100%, I know that much, all right? Now let's go back and look at those limit statements. Look at the first 2 that go together here. We're approaching 2 from the left and 2 from the right, and the y value is 3. That's your whole. That's what we just learned, okay? This is a whole. We have a whole at 2, 3, okay? So if you are a whole, that means you canceled in your function. So you have to have the same on top as on bottom. Before it was an x equals 2, it was x minus 2. I'm going to work it in reverse in a minute to prove to you how I got this. But x minus 2 and x minus 2, those would cancel and give me a whole. Okay? This second limit statement, I'll just tell you, is telling us about a VA. It's telling us we have a VA at x equals negative 4. How do I know that by looking at that? Well, I'm approaching negative 4 from the left and from the right. What a vertical asymptote does, picture it. Okay, so guys, look, this part of my arm is the vertical asymptote. I'm happily traveling from the left, so from the right for you guys. And when I get to it, I can't keep going. It makes me turn. I'm either going to turn up forever or I'm going to turn down forever. Look at this graph. As I approach this vertical asymptote from the left, it stops me. I can't go to the right anymore. So in this case, my branch that's coming from the left turns down towards negative infinity. My branch that's coming from the right gets stopped also at that vertical asymptote, and it makes it go up. So when you see that, you know that that's a VA. VAs don't cancel, okay? So before you were a negative 4, you were a positive 4, and we didn't cancel with the numerator. This is one example of many different ones you could have. We could have had a coefficient in front, like a 3. You could have 5 on top and 5 on the bottom. All 5 would cancel. I'm just making the most basic possibility here. But let me prove to you what we just did by working in reverse. If I gave you this problem and I said, what can x not be? You'd say, x can't be 2 or negative 4, right? That's the two numbers we can't be. Oh, we would have a whole at 2 something, right? Because it cancels, and we'd have a VA at x equals negative 4. So I'm just showing you in reverse. Remember, we have to be able to go from factored form to zeros or zeros to factors. We have to be able to toggle between them by moving it back across the equal sign. Let's look at another one. Okay, we have, we're approaching negative 1 from the left, negative 1 from the right, and our y value is 2. That's a whole. Recognize it. Negative 1, 2. And this one would be a VA, because as we approach 3 from the left and the right, we're going up towards positive infinity. Both branches are just going to hit that hit that vertical asymptote, and they both turned up, okay? And so that means we're going to have a VA at x equals 3. Now, what is that going to look like in a function? Let's create what we know for sure. If you cancel, you're a whole. If you're left, you're a VA. We have a whole at x equals negative 1. Before you were a 0 of negative 1, you were a positive 1, right? Then you set it equal to 0 and solve and got negative 1. And if you're a whole, you have to have the same number on top, or you have to cancel, right? So that's one really basic way of writing that. Those would cancel and make a whole at negative 1. The x equals 3 used to be x minus 3 before we set it equal to 0 and solve, right? 3 is the number that would make the denominator 0. And we don't want to put 1 in the numerator because it's left in the denominator. Okay? To get the y intercept. Wait, what? Yes. So what she's saying is, if we actually did all this, we would have to get a 2 for the y value of the whole. Very good thinking. I'm just going really basic. Just assigning the jobs with the asymptotes in the whole. But you're right. We could definitely do a lot more and make this exact. Okay? Good thinking. That's impressive. I was going to do that, but I'm not. Okay, last example. This is putting it all together. Okay? We're given a rational function, and we're going to answer a bunch of questions about it. So we're going to start the way we start these every time. What can x not be? X cannot be 2 or 3, right? The two numbers that make my denominator 0. The x minus 3 is going to cancel, and the x equals 2 is not going to cancel. So I'm going to fill those in. I'm going to have a VA. Well, I'll write it up here. I'll keep it the same. I canceled, so I'm going to have a whole at 3 something, right? I know, I looked ahead. I'm going to have to find the coordinates, so, we could have written x equals 3, but I'm going to have to find it. It canceled, and we have a VA at x equals 2, okay? All right, let's see what questions they're going to ask us. First is simplified form, right? So that would be f of x equals whatever's left after I canceled. There's my simplified form, right? The coordinates of the whole. Well, we know the x value is 3. We need a y value. Remember, we plug into the simplified form. So I'm just going to plug a 3 in. Nine minus 13 is negative 4. 3 minus 2 is 1. Negative 4. And it's already graphed for us. 3, negative 4. There's that whole. Okay, we're going to save domain and range for last. Vertical asymptote. X equals 2. Let's put it on the graph. I don't know if it's on yours, but it's not on mine. And we can look at the graph and see that there's a horizontal asymptote at y equals 3. But let's review why. When you are looking for the HA, we look at the degree of the numerator versus the degree of the denominator. Remember that? And we do it on the simplified version, okay? So remember, when the numerator's degree is equal to the denominator's degree, we then look at the leading coefficients. 3 over 1 is 3, okay? So 1, 1, same, 3 over 1 is 3. Domain and range. This, when we do it the first time, you're going to be a little confused. By the time we get to the homework and we do those together, everyone gets it, I promise, okay? So domain is the x values, all right? So and these are the easiest to do by looking at the graph. Even I would have a hard time doing it with just looking at numbers. When I have my graph, then I can just visually see my domain and range. So remember, domains are your x's. We always start furthest to the left. So that's negative infinity, right? That's this. So as we travel, what's the first x value we get to that causes us a problem? So I'm traveling. Where's an x value that's going to cause me a problem? 2, right? 2, I can't get to 2. 2 is omitted from the graph. So I'm going to put that in my domain, but with parentheses, because it's not included. Everything up until 2 is. Then we put the union symbol, and we start again at 2. Now we're on this part of the graph. We're not including it, but everything directly to the right of 2. I call that like jumping over, like we jumped over the 2. What's the next x value that gives us a problem? 3. Good. Remember, this is bad. This point is not part of the graph. It's excluded. I'm excluding it and jumping over it. Those are the only 2 places on the graph that cause us a problem as far as the domain. That vertical asymptote and the x value of the whole. After that, we're home free and we keep going to the right forever. So what causes us a problem for our domain would be the VA and the x value of the whole. Those are the 2 x values. And I want you to see it visually. Like, don't memorize that. Think about it. What's happening as I go. And we'll do it again in the homework. Let's talk about the range. We're starting at the bottom, right? That starts down, and we start moving up. Where is there a y value that causes a problem for me in this graph? No, not 3. Y value. -4, right? That y value of -4 is left out. So let's jump over it. What's the next y value that causes a problem? This one's 3, yes. Let's jump over 3. And after that, we're good. Okay, so the HA causes a problem for us and the y value of the whole. Last thing, let's do some limits. They're already written out for us. We just have to answer them. So, you have to be able to read these and understand what part of the graph they're talking about. So look at these first 2. Stay with me. It's saying what is happening as x approaches negative infinity and positive infinity. That's the ends of the graph. Look, what's happening here and here as x approaches negative infinity and y infinity, positive infinity. What is the y value that they're both approaching? Where is it? It's going down, right? Is it going to go down forever? It can't go down forever, right? It's approaching 3. We are approaching 3 because, and same thing on the right, as we go towards positive infinity, our y values are getting as close as they can to 3. We've called HAs end behavior asymptotes before because HAs give us our end behavior. That horizontal asymptote is blocking the ends from going up or down forever, okay? Look at the next one. What's happening at x equals 2? That's our vertical asymptote. So as we approach 2 from the left, what are all my y values doing? Increasing forever. I love that you used that word. And then as we approach 2 from the right, my y values are decreasing forever. That's my vertical asymptote. And this is my whole, right? X is 3, what's the y value? And it didn't say from the left or right. So if it doesn't say from the left or right, it just means from the left and right. So like as we approach 3, what y value are we getting really, really close to? -4. Okay? Now I know I threw a lot at you. We're going to practice these together. Find this page. All right. I'm going to do 19 and 20 with you, and then the rest of them are multiple choice. We good? Everyone have it written down so I can take this down? That's all that matters. Did you write this down? You got it? Okay. 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 Notice we have to graph this one. We're going to make it really simple. Don't worry. Start every problem the same way. What can x not be? +3, right? There's only one number. There's only one problem, 3, okay? Let's figure out what type of problem. Well, we have 1 on top, right? So we can cancel that one, and there's 2 on the bottom. That's going to leave us with 1 on the bottom. Is that a VA or a whole? It's a VA. We're going to have a VA at x = 3. So you can just put it here if you want. And we don't have a whole. You don't have to. It's okay. There's nothing that canceled completely. Okay, let's do horizontal asymptote. Oh, simplified form, sorry. Simplified form would be whatever's left after we canceled. So that's f of x equals, there's an x + 4 on top and an x - 3 on the bottom. That's simplified form. We're going to use that to find our HA. Again, degree of your numerator, degree of your denominator. When those are the same, you then look at the leading coefficients, which of course are just 1. So that would be y equals 1/1 or 1. We're not going to do the y-intercept. You're welcome. X-intercepts come from the numerator. X + 4 is in my numerator, and it didn't cancel. There was never an x + 4 in the denominator that could have affected its status as an x-intercept. So x + 4, set it equal to 0, you get -4. Intercepts are points. So what's the y value of an x-intercept? 0, right? If you're on the x-axis, your y value is 0, always. And remember what I said, domain and range, don't bother dealing with it till you have the graph, okay? We're going to make this really, really simple to graph. Easier than, I'll remind you what you had to do in Algebra 2. You don't have to do all that stuff. All right, put your asymptotes on there. Vertical asymptote on x = 3. Horizontal asymptote at y = 1. X-intercept at -4, 0. Now that we've established that there's a point, like think about the asymptotes kind of skewed your x and y axis. We still have like 4 quadrants, 1, 2, 3, 4. So in our like new quadrant 3, we have a point. You can just go ahead and sketch your branch in there. It's not exact. It doesn't have to be. These are very complicated graphs with lots of decimals. We don't need them. We don't care. Okay? I've also told you that these graphs can be very different. Every graph is different. The ones that we're going to graph are very basic, and they're always going to have curvies in opposite quadrants. So since we have one here, we know there's going to be one up here. In Algebra 2, you would have, don't write this, you would have had to like make an XY chart and pick values over here and plug in and then find the exact points, which are decimals, okay? We aren't going to worry about that. We're just going to keep it nice and simple and just know that there's going to be a branch over here. If you wanted to make this more exact, by all means, go ahead. But I'm keeping it very simple because that's not what this is about. It's not really about being able to graph them. It's about being able to pull information from the graph, okay? Now we can do our domain and range. It's going to be a little shorter than the one we just did because we don't have a hole that's going to cause problems for us. So let's look at the graph. Our domain as we come from the left, right? So that's negative infinity. We're traveling, we're traveling. What's the first x value that's going to give us a problem? 3, right? We're going. We're getting as close as we can to this 3, but we can't touch it. It's not included. It's an asymptote. Let's jump over it. And then there's no other x values. There's no hole in this problem that we have to worry about. So we're home free now. We can continue on to the right forever. Okay. Good. Okay. And then for the range, negative infinity, up to what? What's the first y value that causes us to stop? 1. Let's jump over it. Is there anything else blocking us? Nope. Okay. Evan, are you starting to get it better? These are horrible. I hate teaching this. Every class Algebra 2 is worse because of all the XY charts. But these are just not fun. We'll be done with them soon, okay? Unit 1, I think, is the hardest unit of the 3 units, believe it or not. Everyone thinks trig is going to be really hard. Unit 3 is all the unit circle stuff. It's my favorite. Oh, calculus is algebra and trig put together. Trig is my favorite thing in the world. What? We're roughly 3, there's only 3 units, okay? We're almost done with unit 1, believe it or not. And so it's roughly unit 1 is quarter 1, unit 2 is quarter 2, although it spills over a little bit. And then unit 3 is quarter 3, it spills over a little into unit 4. And then we have a ton of review time. Yeah. All right, so x can't be -1 or 4. Come on, guys. -1 and 4. What type of problems are they? Those cancel. So I'm going to have a hole at, -1 something. We'll get to that, right? Because we canceled. And we'll have a vertical asymptote at 4 because it's left. Let's write the simplified form. Whatever's left after you canceled is your simplified form. And we're going to use that to find our HA and the Y value of our hole. Okay? So the HA is degree of the numerator, degree of the denominator, 1. So whenever they're the same, we then look at the coefficients. The coefficient on top is 2, coefficient on the 1 is 1 on the bottom, and then 2 over 1 is 2. Don't forget to put Y equals 2. We're not going to do the y-intercept. Is there anything in the numerator that's got an x in it that wasn't affected by the denominator? Yeah. So we're going to have an x-intercept at 3, 0. The 2 is a factor, but it doesn't have an x from it. You can't set 2 equal to 0 and solve it. But if you set x minus 3 equal to 0 and solve it, you would get 3. Okay. Then let's find the y value of our hole. I just don't have any space. I'm going to plug -1 in. That gets me 2 times -4 over -5. $1.6. Or you could leave it in fraction form, okay? But we are going to have to graph it, so where the heck is 8/5? You know what I mean? It's one and a little bit more, right? We save domain and range till we have the graph to look at. It's the easiest way, right? So I'm going to start by putting my asymptotes, and everything I just found is going to go on the graph, basically. So x equals 4, so I have a vertical asymptote at x equals 4. A horizontal asymptote at y equals 2. I have an x-intercept at 3, 0. So an x-intercept is a closed circle. It is part of the graph. It is included, not excluded, right? But we do have an open circle at -1, 1.6. There's lots of decimals in these. That's why we hate them so much, one of the reasons. Because it's a hole. That's what a hole is. You're excluded, okay? I'm going to tell you the truth, though. I always forget to put my hole. I'll put the graph and be like, oh, I forgot to put the hole. I'll show you how to handle that. So you can see that we're going to have a branch in this quadrant. If you forgot the hole, you could, like I always do, I'll forget the hole and I'll just make my graph. You could just go right over it and show me that you meant to put a hole there, okay? So this is not perfection stuff, okay? And then, like I said, we could get real deep into XY charts and stuff. We're going to just know that there's another branch in the opposite quadrant, diagonal quadrant. Even though there's all different types of them, this is the only type we're going to deal with, okay? Now we can do domain and range. Visually makes it so much easier, in my opinion. Maybe if you're not a visual person, it's not easier for you, but figure out what works for you. Okay, so start traveling on the graph from the left. What's the first x value we get to that causes a problem for us? X value. 4 is a problem. You're right, but there's one that comes across earlier. Yes, don't forget you have a hole here. Remember, Evan, a hole is excluded. That would give us a 0. Remember, -1 would give us a 0 in our denominator. So it's not part of the graph. So we have to skip over -1. Then, like Evan said, 4 is the next x value that blocks us. We can't touch it. We have to skip over 4, and then we're good. Do the same thing with the y values. From -infinity, what's the first y value we get to that causes us a problem? 1.6. Jump over it. What's the next y value that causes a problem? 2. Jump over it. And then keep going. They look really gnarly. Don't be afraid of those. We're going to practice a lot. Don't worry. Okay? I don't know how much time you have. Oh, you guys have a good amount of time. Like I said, you might finish your homework. The last few are multiple choice. Don't just copy my answers, okay? Really try.
Good morning, Countryside High School. We would like to remind you that we're going to do our theme week for Dress Up Day next week, so everyone can be given time to get proper dress going, and we'll have posters put up around the school. The homecoming dance is going to be the 12th of October, but tonight, all homecoming course, please report to the west end of the field to find Mrs. Walker at 7:15 p.m. If you want to be in the homecoming court and presented at halftime, you need to be at the game, dressed at 7:15 tonight. We are going to announce
tonight.
Have a very good day.
You what? They usually. Yeah, I think they're selling them at lunch, or you can buy them when you get there. I think they're selling them at lunch.